Well, welcome back to our course, Computer Organization and Architecture. This is going to be our last chapter lecture. And so we're coming to the end of quite a journey. So keep that in mind. And so we're going to be talking about multi-core computers. And just as a reminder to give you a perspective, this is the second and last of the two lectures for this section on parallel organization. So let's go ahead and get into the details here. So here is an outline of what we'll cover, and then we'll come back to this chart at the end, like we typically have done. So for multi-core computers, we'll be talking about hardware performance issues and the ways that we can deal with that. We'll talk about software performance issues and how doing multi-core capability can be a benefit. We'll then talk about examples of a couple of different types of processors. We'll talk about the Intel Core, the i7, and so we'll see how that works. We'll talk about the IBM Z13 mainframe and what they do on this perspective. Then let's talk about the multi-core organization, the level of caches, simultaneous multi-threading, some of these concepts that we've already talked about, but let's put it into a specific context. We'll talk about heterogeneous multi-core organizations. So not everything is the same. And then we'll talk about another specific processor. We'll talk about the ARM Cortex-A15 MP core. All right, well, let's go ahead and get into the material. So the organizational changes in processor design has primarily focused on exploring ILP so that more work is done in each clock cycle. These changes include chronological order. And so here is what we're trying to get a sense about that with figure 21.1. So let's talk about a few things. Pipelining. And so individual instructions are executed through a pipeline of stages so that while one instruction is executing in one stage of the pipeline, another instruction is executing in another stage of the pipeline. Superscalar. So we've talked about these things, but maybe this is good to be thinking about this in context. So superscalar, multiple pipelines are constructed by replicating execution resources. This enables parallel execution of instructions in parallel pipelines so long as hazards are avoided. We also have simultaneous multi-threading, SMT. The register banks are replicated so that multiple threads can share the use of pipeline resources. Each one of these innovations, the designers have over the years attempted to increase the performance of the system by adding complexity. In the case of pipelining, simple 3-stage pipelines were replaced by pipelines with 5 stages until Pentium 4 core had 31 stages for some instructions, so Pentium 4 Prescott. There is a practical limit to how far this trend can be taken because with more stages, there is the need for more logic, more interconnections, and more control signals. With superscalar organization, and increased performance can be achieved by increasing the number of parallel pipelines. Again, there are diminishing returns as the number of pipelines increases. More logic is required to manage hazards and to stage instruction resources. Eventually, a single thread of execution reaches a point where hazards and resource dependencies prevent the full use of the multiple pipelines available. Also, compiled with binary code rarely expose enough ILP to take advantage of more than about 6 parallel pipelines. The same point of diminishing returns is reached with SMT, as the complexity of managing multiple threads over a set of pipelines limits the number of threads and number of pipelines that can be effectively utilized. SMT's advantages lie in the fact that 2 or more program streams can be searched for available ILP. There is a related set of problems dealing with the design and fabrication of the computer chip. The increase in complexity to deal with all of the logical issues related to very long pipelines multiple superscaling pipelines, and multiple SMT register banks means that increasing amounts of the chip area are occupied with coordinating and signal transfer logic. This increases the difficulty of designing, fabricating, and debugging the chip. The increasingly difficult engineering challenge related to processor logic is one of the reasons that an increasing fraction of the processor chip is devoted to the simpler memory logic. Power issues discussed next provide another reason. So to maintain the trend of higher performance as the number of transistors per chip rises, designers have resorted to more elaborate processors designs, pipelining, superscalar, and SMT, like we just were talking about, and to higher clock frequencies. Unfortunately, power requirements have grown exponentially as chip density and clock frequency have risen. This is shown in figure 2.2, 21.2, what we're showing here. So let's just keep that in mind. So one way to control power density is to use more of the chip area for cache memory. Memory transistors are smaller and have a power density on the order of magnitude lower than that of logic. So we're showing this in figure 21.2. As chip transistor density has increased, so the percentage of chip area devoted to memory has grown and is now often half of the chip area. Even so, there is still a considerable amount of chip area devoted to processing logic. How to use all those logic transistors is a key design issue, as discussed earlier in the section. There are limits to the effective use of such techniques as superscalar and SMT. In general terms, the experience of recent decades has been encapsulated in a rule of thumb known as Pollack's rule, which states that performance increase is roughly proportional to the square root of increase in complexity. In other words, if you double the logic in a processor core, then it delivers only 40% more performance. In principle, the use of multiple cores has the potential to provide near linear performance improvements with the increase in number of cores, but only for software that can take advantage. Power considerations provide another motive for moving towards a multi-core organization. Because the chip has a huge amount of cache memory, it becomes unlikely that any one thread of execution can effectively use all that memory. Even with SMT, multi-threading is done in a relatively limited fashion and cannot therefore fully exploit a gigantic cache, whereas a number of relatively independent threads or processors has a greater opportunity to take full advantage of the cache memory. The potential performance benefits of a multi-core organization depends on the ability to effectively exploit the parallel resources available to the application. Let us focus first on a single application running on a multi-core system. The law assumes a program with a fraction that is 1 minus f of the execution time involves code that is inherently serial, and a fraction f that involves code that is infinitely parallelizable with no scheduling overhead. This law appears to make the prospect of a multi-core organization attractive. That is figure 21.3a. This is the figure we're showing. Illustrates even a small amount of serial code has a noticeable impact. If only 10% of the code is inherently serial, so f equals 0.9, running the program on a multi-core system with 8 processors yields a performance gain of only a factor of 4.7. In addition, software typically incurs overhead as a result of communication and distribution of work among multiple processors and as a result of cache coherence overhead. This result in a curve where performance peaks and then begins to degrade because of the increased burden of the overhead of using multiple processors. So that's resulting, you have to be doing coordination and operating system management. Figure 21.4b is a representative example of what we can see of what starts to happen when we above a certain threshold, things start to fall off. However, software engineers have been addressing this problem, and there are numerous applications in which it is possible to effectively exploit a multi-core system. And so this has been shown. One of the references talks about it analyzes the effectiveness of multi-core systems on a set of database applications in which great attention was paid to reduce the serial fraction with the hardware architectures, operating systems, middleware, and the database application software. So in this figure 21.4, it shows the result. As the example shows, database management systems and database applications are one area in which multi-core systems can be used effectively. Many kinds of servers can also effectively use the parallel multi-core organization because servers typically handle numerous relatively independent transactions in parallel. In addition to general purpose server software, a number of classes of applications benefit directly from the ability to scale through with the number of cores. And so one of the references in the text, it provides this list, and so we list the following examples. For multi-thread native applications, which is dealing with thread level parallelisms, multi-threaded applications are characterized by having a small number of highly threaded processes. There's multi-process applications. This is dealing with process level parallelisms. Process applications are characterized by the presence of many single threaded processes. Then we have Java applications. Java applications embrace threading in a fundamental way. Not only does the Java language greatly facilitate multi-threaded applications, but the Java virtual machine is a multi-threaded process that provides scheduling and memory management for Java applications. And we have multi-instant applications. This is application level parallelisms. Even if an individual application does not scale to take advantage of a large number of threads, it is still possible to gain from multi-core architectures by running multiple instances of the application in parallel. If multiple application instances require some degree of isolation, virtualization technology for the hardware of the operating system can be used to provide each of them its own separate and secure domain. So before turning to an example, we want to elaborate on the topic of thread level parallelism by introducing the concept of threading granularity, which can be defined as a minimal unit of work that can be beneficially parallelized. In general, the finer the granularity that the system enables, the less constrained is the programmer in parallelizing a program. Consequently, finer grain threading systems allow parallelisms in more situations than coarse grain ones. The choice of the target granularity of an architecture involves an inherent trade-off. On the one hand, the finer grain systems are preferable because of the flexibility they afford to the programmer. But on the other hand, the finer the threading granularity, the more significant part of the execution is taken by the threading system overhead. So here we're showing an illustration, a hybrid threading for rendering module. So Value is an entertainment and technology company that has developed a number of popular games, as well as the Source engine, one of the most widely played games engines available. Source is an animation engine used by Value for its games and licensed for other game developers. Value has reprogrammed the Source engine software to use multi-threading to exploit the power of multi-core processor chips from Intel and AMD. The revised source engine code provides more powerful support for value games such as Half-Life 2. So Value found that through coarse threading, it could achieve up to twice the performance across the two processors compared to executing on a single processor. But this performance gain could only be achieved with contrived cases. For real-world game playing, the improvement was on the order of a factor of 1.2. Value also found that effective use of fine-grained threading was difficult. The time per work unit can be variable, and managing the timeline of outcomes and consequences involve complex programming. Value found that a hybrid threading approach was the most promising and would scale the best as multi-core systems with 8 or 16 processors became available. Value identified systems that operate very effectively when assigned to a single processor permanently. An example is sound mixing, which has little user interactions, is not constrained by the frame configuration of Windows, and works on its own set of data. Other modules, such as scene rendering, can be organized into a number of threads so that the module can execute on a single processor, but achieve greater performance as it is spread out over more and more processors. Figure 21.5 that we're showing here illustrates the thread structure for the rendering module. In this hierarchical structure, higher level threads spawn lower level threads as needed. The rendering module relies on a critical part of the source engine, the word list, which is a database representation of the visual elements in the game world. The first task is to determine what are the areas of the world that need to be rendered. The next task is to determine what objects are in the scene as viewed from multiple angles. Then comes the processor intensive work. The rendering module has to work out the rendering of each object from multiple points of view, such as the player view, the view of the TV monitors, and the point of view of reflection in water. Some of the key elements of the threading strategy for the rendering modules are listed below, and so let's just go through these. So construct scene rendering list for multiple scenes in parallel. For example, the world and its reflection in water. Overlap graphics simulation. Compute character bone transformations for all characters in all scenes in parallel. Allow multiple threads to draw in parallel. The designers found that simply locking key databases such as the world list for a thread was too inefficient. Over 95% of the time, a thread is trying to read from a data set, and only 5% of the time at most is spent in writing to the data set. Thus, a concurrency mechanism known as single writer, multiple readers model works effectively. Figure 21.6 shows 4 general organizations for multi-core systems. Figure 21.6a is the organization found in some of the earlier multi-core computer chips and is still seen in embedded chips. In this organization, the only on-chip cache is L1, with each core having its own dedicated L1 cache. Almost invariably, the P1 cache is divided into instructions and data caches. An example of this organization is the ARM11 MP core. The organization of 21B is also one in which there is no on-chip cache sharing. In this, there is enough area available on the chip to allow for L2 cache. An example of this organization is the AMD Opteron. Figure 21.6c shows a similar allocation of chip spaces to memory, but with the use of a shared L2 cache. The Intel Core Duo has this organization. Finally, as the amount of cache memory available on the chip continues to grow, performance considerations dictate splitting off a separate shared L3 cache. This is what we're showing in figure 21.6d, with dedicated L1 and L2 cache for each core processor. The Intel Core i7 is an example of this organization. The use of shared higher level cache on the chip has several advantages over exclusive reliance on dedicated caching. So number one, constructive interference can reduce overall miss rates. That is, if a thread on one core accesses a main memory location, this brings the line containing the reference location into the shared cache. If a thread on another core soon thereafter accesses the same memory block, the memory location will already be available in the shared on-chip cache. Two, a related advantage is the data shared by multiple cores is not replicated at the shared cache level. Three, with proper line replacement algorithms, the amount of shared cache allocated to each core is dynamic so that threads that have less locality, that is large working sets, can employ more cache. Four, inter-core communication is easy to implement via shared memory locations. And five, the use of shared higher level cache confines the cache coherency problem to the lower cache levels, which may provide some additional performance advantages. A potential advantage is to have only dedicated L2 cache on the chip is that each core enjoys more rapid access to the private L2 cache. This is advantageous for threads that exhibit strong locality. As both the amount of memory available and the number of cores grow, the use of shared L3 cache combined with the dedicated pre-core L2 caches in figure 21.6D seems likely to provide better performance than simply a massive shared L2 cache on a very large dedicated L2 caches with no on-chip L3. An example of this arrangement is a Xeon E5 2600 and 4600 chip processor. That's something you can go back to figure 8.16 if you wanted to look into that further. Another organizational design decision is in a multi-core system is whether the individual cores will be superscalar or will implement simultaneous multi-threading, SMT. For example, the Intel Core Dual uses superscalar cores, where the Intel Core i7 uses SMT cores. SMT has the effect of scaling up the number of hardware level threads that the multi-core system supports. Thus, a multi-core system with 4 cores and SMT that supports 4 simultaneous threads in each core appears the same to the application level as a multi-core system with 16 cores. As software is developed to more fully exploit parallel resources, an SMT approach appears to be the more attractive than a superscalar approach. Typical case for the use of multi-core cores in a chip with multiple identical cores known as homogeneous multi-core organization to achieve better results in terms of performance and or power consumption and increasingly popular design choice is heterogeneous multi-core organization, which refers to a processor chips that includes more than one kind of core. So in this section, we will look at 2 applications to heterogeneous multi-core organization. The approach that has received the most industry attention is the use of cores that have distinct ISAs. Typically, this involves mixing conventional cores referred to in this context as CPUs with specialized cores optimized for certain types of data or applications. Most often, the additional cores are optimized to deal with vector and matrix data processing. The most prominent trend in terms of heterogeneous multi-core design is the use of both CPUs and graphic processor units, GPUs, on the same chip. Briefly, GPUs are characterized by the ability to support thousands of parallel execution threads. Thus, CPUs are well matched to applications that process large amounts of vector and matrix data. Initially aimed at improving the performance of graphic applications, thanks to easy to adopt programming modules such as CUDA, which stands for Compute unified device architecture, these new processors are increasingly being applied to improve the performance of general purpose and scientific applications that involves large numbers of repetitive operations on structured data. To deal with the diversity of target applications in today's computing environment, multi-core containing both GPUs and CPUs have the potential to enhance performance. This heterogeneous mix, however, presents issues of coordination and correctness. Figure 21.7 is a typical multi-core processor organization. Multiple CPUs and GPUs share on-chip resources such as the last level cache, LLC, interconnection network, and memory controllers. Most critical is the way in which cache management policies provide effective sharing of the LLC. The difference in cache sensitivity and memory access rate between GPUs and CPUs create significant challenges to the efficient sharing of the LLC. Table 21.1 illustrates the potential performance benefits of combining CPUs and GPUs for scientific applications. This table shows the basic operating parameters of an AMD chip, the A10 5800K. For floating point calculations, the CPU's performance at 121.6 gigaflops is dwarfed by the GPU, which offers 614 gigaflops to applications that can utilize the resource effectively. Whether it is scientific applications or traditional graphic processing, the key to leverage the added GPU processors is to consider the time needed to transfer a block of data to the GPU, process it, then return the results to the main application thread. In earlier implementations of the chips, the incorporated GPU's physical memory is partitioned between the CPU and GPU. If an application thread is running on a CPU, that demands GPU processing. The CPU explicitly copies the data to the GPU memory. The GPU completes the computation and then copies the results back to the CPU memory. Issues of cache coherence across CPU and GPU memory caches do not arise because the memory is partitions. On the other hand, the physical handling of data back and forth results in performance penalties. A number of research and development efforts are underway to improve performance over that described in the preceding discussion that I just have, of which the most notable is the initiative by the Heterogeneous System Architecture, HSA, Foundation. Each feature of the HSA approach includes the following. The entire virtual memory space is visible to both CPU and GPUs. Both CPU and GPUs can access and allocate any location in the system's virtual memory space. 2, the virtual memory system brings in pages to physical main memory as needed. 3, a coherent memory policy ensures that CPU and GPU caches both see an up-to-date view of data. And 4, a unified programming interface that enables users to exploit the parallel capabilities of the GPU within programs that rely on the GPU execution as well. The overall objective is to allow programmers to write applications that exploit the serial power of GPUs and the parallel processing power of GPUs seamlessly with efficient coordination as the operating system and at the operating system and hardware level. As mentioned, this is an ongoing area of research and development. Another common example of heterogeneous multi-core chip is a mixture of CPUs and digital signal processors, DSPs. A DSP provides ultra-fast instruction sequencing, such as shift and add, multiply and add, which are commonly used in math-intensive digital signal processing applications. DSPs are used to process analog data from sources such as sound, weather satellites, and earthquake monitors. Signals are converted into digital data and analyzed using various algorithms such as fast Fourier transform. DSP cores are widely used in a myriad of devices, including cell phones, sound cards, fax machines, modems, hard disk, and digital TVs. As a good representative example, figure 21H shows a recent version of the Texas Instrument K2H SoC platform. This heterogeneous multi-core processor delivers power-efficient processing solutions for high-end imaging applications. TI lists the performance as delivering up to 352 Gmax, 198 gigaflops, and 19,600 MIPS. Gmax stands for giga, that is millions of, multiply accompanying operations per second, common measure of DSP performance. Target applications for these systems include industrial automation, video surveillance, high-end inspection systems, industrial printers/scanners, and currency/counterfeit detection. The TI system includes 4 ARM Cortex-A15 cores and 8 TI C66X DSP cores. Each DSP core contains 32 kilobyte of L1 data cache and 32 kilobyte of L1 program, that is instruction cache. In addition, each DSP has 1 megabyte of dedicated SRAM memory that can be configured as an L2 cache, all main memory, or a mixture of the two. The portion configured as main memory functions as a, quote, local main memory, referred to simply as SRAM. This local main memory can be used for temporary data, avoiding the need for traffic between cache and off-chip memory. The L2 cache of each of the 8 DSP cores is dedicated rather than shared with the other DSP cores. This is typical for multi-core DSP organization. Each DSP works on a separate block of data in parallel, so there is little need for data sharing. Each ARM Cortex-A15 CPU core has 32 kilobytes L1 data and program caches, and the 4 cores share a 4 megabyte L2 cache. The 6 megabyte multi-core shared memory, or you can, the abbreviation is MSM, is always configured as all SRAM. That is, it believes that main memory rather than cache is able, that is, it behaves like main memory rather than cache. It can be configured to feed directly the L1 DSP and CPU caches, or to feed the L2 DSP and CPU caches. This configuration decision depends on the expected application profile. So that's an important point. We're seeing these different designs that are optimized for a specific area of application and may not work generally across the board as a general processor. So the multi-core shared memory controller, the MSMC, manages traffic among ARM cores, DSP, DMA, other mastering peripherals, and the external memory interface, EMIF. MSMC controls access to the MSN, which is accessible by all the cores and the mastering peripherals on the device. Another recent approach to heterogeneous multi-core organization is the use of multiple cores that have equivalent ISAs but vary in performance or power efficiency. The leading example of this is ARM's Big Little architecture, which we examine here in this section. Figure 21.9, which we're showing now, illustrates this architecture. The figure shows a multi-core processor chip containing 2 high-performance Cortex-A15 cores and 2 lower-performance, lower-powered consuming Cortex-A7 cores. The A7 cores handle less computationally intensive tasks such as background processing, playing music, sending text, and making phone calls. The A15 cores are involved in high-intensity tasks such as video, gaming, and navigation. The Big Little architecture is aimed at the smartphone and tablet markets. These are devices whose performance demands from users are increasingly as a much faster rate than a capacity of batteries or the power savings from semiconductor process advances. The usage pattern for smartphone and tablets is quite dynamic. Periods of processing intense tasks such as gaming and web browsing alternate with typical longer periods of low processing and intensity tasks such as texting, email, and audio. The big little architecture takes advantage of this variation in required performance. The A15 is designed for maximum performance with the mobile power budget. The A7 processor is designed for maximum efficiency and high enough performance to address all but the most intense periods of work. The A7 is far simpler and less powerful than the A15, but its simplicity requires far fewer transistors than does the A15's complexity, and fewer transistors requires less energy to operate. The difference between the A7 and A15 cores are seen most clearly by examining their instruction pipelines as shown in 2110, which we're showing right now. The A7 is an in-order CPU with a pipeline length of 8 to 10 stages. It has a single queue for all execution units, and 2 instructions can be sent to its 5 execution units per clock cycle. The A15, on the other hand, is an out-of-order processor with a pipeline length of 15 to 24 stages. Each of the 8 execution units has its own multi-stage queue, and 3 instructions can be processed per clock cycle. You may want to pause the video and look at this just to get a better sense of that, but you can see that they're definitely optimized for different complementary things. The energy consumed by the execution of an instruction is partially related to the number of pipeline stages it must travel. Therefore, a significant difference in energy consumption between the Cortex-A15 and Cortex-A7 comes from the different pipeline complexity. Across a range of benchmarks, the Cortex-A15 delivers roughly twice the performance of the Cortex-A7 per unit megahertz, and the Cortex-A7 is roughly 3 times as energy efficient as the Cortex-A15 in completing the same workloads. This performance trade-off is illustrated in figure 2111, which we're showing here with this figure. Typically, a heterogeneous multi-core processor will feature a dedicated L2 cache assigned to the different processor types. We see that in the general depiction of a CPU/GPU scheme of figure 21.7. Because the CPU and GPU are engaged in quite different tasks, it makes sense that each has its own L2 cache shared among similar CPUs. We also see that in the big little architecture that we were talking about with figure 21.9, in which the A7 cores share an L2 cache and the A15 cores share a separate L2 cache. When multiple caches exist, there is a need for cache coherence schemes to avoid access to invalid data. Cache coherence may be addressed with software-based techniques. In the case where the cache contains stale data, the cached copy may be invalidated and reread from the memory when needed again. When memory contains stale data due to a write-back cache containing dirty data, the cache may be cleaned by forcing write-back to memory. Any other cache copies that may exist in other caches must be invalidated. This software burden consumes too many resources in the SoC chip, leading to the use of hardware cache coherent implementations, especially in heterogeneous multi-core processors. As described in Chapter 20, there are 2 main approaches to hardware implemented cache coherency, directory protocols and Snoopy protocols. ARM has developed a hardware coherency capability called ACE, Advanced Extensible Interface Coherence Extensions, that can be configured to implement either directory or Snoopy approaches, or even a combination. ACE has been designed to support a wide range of coherent masters with different capabilities. ACE supports coherency between dissimilar processors such as the Cortex-A15 and the Cortex-A7 processors, enabling ARM big little technology. It supports I/O coherency for uncached masters, supports masters with different cache line sizes, different internal cache state models, and masters with write back or write through caches. As another example, ACE is implemented in the memory subsystem memory controller, the MSMC, in the TI SoC chip of figure 21.8. MSMC supports hardware cache coherence between the ARM core pack L1/L2 caches and EDMA/IO peripherals for the shared SRAM and DDR spaces. This feature allows the sharing of MSMC, SRAM, and DDR data spaces by these masters on the chip without having to use explicit software cache maintenance techniques. ACE makes use of 5-staged cache model. In each cache, each line is either valid or invalid. If a line is valid, it can be in one of 4 states defined by 2 dimensions. A line may contain data that are shared or unique. A shared line contains data from a region of external, that is main memory, that is potentially shareable. A unique line contains data from a region of memory that is dedicated to the core owning this cache. And the line is either clean or dirty, generally meaning either memory contains the latest, most up-to-date data that the cache line is merely a copy of memory. Or if it is dirty, then the cache line is the latest, most up-to-date data, and it must be written back to memory at some stage. The one exception to the above description is when multiple caches share a line and it's dirty. In this case, all caches must contain the latest data value at all times, but only one may be in the shared/dirty state, the others being held in the shared/clean state. The shared/dirty state is then used to indicate which cache has responsibility for writing the data back to memory, and shared/clean is more accurately described as meaning data is shared, but there is no need to write it back to memory. The ACE states correspond to the cache coherency model with 5 states known as MOSI, M-O-E-S-I. So table 21.2 compares the MOSI model with the MESI model, which was described in chapter 20. So we can see that they have the same general categories, but what can be done is a little bit different with these different factors. I'm not going to go through this. You can pause the video and review that as long as you would like. So Intel has produced a number of multi-core products in recent years. So in this section, we will look at the Intel Core i7-5660X. The general structure of the Intel Core i7 is shown in the figure 2113. Each core has its own dedicated L2 cache, and the 8 cores share a 20 megabyte L3 cache. One mechanism Intel uses to make its caches more effective is prefetching, in which the hardware examines memory access patterns and attempts to fill the cache speculatively with data that likely will be requested soon. So the Core i7 chip supports 4 forms of external communication to the other chips. The DDR4 memory controller brings the memory controller for the DDR main memory onto the chip. The interface supports 3 channels that are 8 bytes wide for a total bus width of 256 bits for an aggregate data rate of up to 64 gigabytes per second. With the memory controller on the chip, the front side bus is illuminated. The PCI Express is a peripheral bus. It enables high-speed communication among connected processor chips. The PCI chip link operates at 8 gigatransfers per second. So at 40 bits per transfer, that adds up to 40 gigabytes per second. So we have already seen 2 examples of heterogeneous multi-core processors using the ARM cores. Section 21.4, the big little architecture, which uses a combination of the ARM Cortex A7 and the Cortex A15 cores, and the Texas Instruments DSP SoC architecture, which combines the Cortex A15 cores with the TI DSP cores. So in this section, we will introduce the Cortex A15 MP core multi-core chip, which is a homogeneous multi-core processor using multiple A15 cores. The A15 MP core is a high-performance chip targeted at applications including mobile computing, high-end digital home servers, and wireless infrastructure. So the figure we're showing here, figure 2114, presents a block diagram of the Cortex A15 MP core. The key elements of the system are the following. First, there's generic interrupt controller, the GIC. It handles interrupts detection and interrupt prioritization. The GIC distributes interrupts to individual cores. Then there's the debug unit interface. The debug unit enables an external debug host to stop the program execution, examine and alter process and coprocessor states, examine and alter memory and input/output peripheral states, and to restart the processor. There's also a generic timer. Each core has its own private timer that can generate interrupts. There's a trace, which supports performance monitoring and program trace tools. There's the core, a single ARM Cortex A15 core. There's the L1 cache. Each core has its own dedicated L1 data cache and L1 instruction cache. There's the L2 cache, the shared L2 cache. Memory system services L1 instruction and data cache misses from each core. And finally, there's a Snoop controller unit, the SCU, which is responsible for maintaining the L1/L2 cache coherency. The GIC correlates interrupts from a large number of sources. It provides masking of interrupts, prioritization of the interrupts, distribution of interrupts to the targeted A15 cores, tracking the status of interrupts, and generation of interrupts by the software. The GIC is a single functional unit that is placed in the system alongside A15 cores. This enables a number of interrupts supported in the system to be independent of the A15 core design. The GIC is memory mapped, that is control registers for the GIC are defined relative to a main memory base address. The GIC is accessed by the A15 cores using a private interface through the SCU. So the GIC is designed to satisfy 2 functional requirements. First, to provide a means of routing an interrupt request to a single CPU or multiple CPUs as required. And second, to provide a means of interprocessor communication so that a thread on one CPU can cause activity by a thread on another CPU. As an example that makes use of both requirements, consider a multi-thread application that has threads running on multiple processors. Suppose the application allocates some virtual memory. To maintain consistency, the operating system must update memory translation tables on all processors. the operating system could update the table on the processor where the virtual memory allocation took place, and then issue an interrupt to all other processors running this application. The other processors could then use this interrupt ID to determine that they need to update their memory translation tables. The GIC can route and interrupt to one or more CPUs in the following three ways. An interrupt can be directed to a specific processor only, and an interrupt can be directed to a defined group of processors. The MP core views the first processor to accept the interrupt, typically the least loaded, as being best positioned to handle the interrupt. And finally, an interrupt can be directed to all processors. From the point of view of software running on a particular CPU, the operating system can generate an interrupt to all but self, or to specific other CPUs. For communication between threads running on different CPUs, the interrupt mechanism is typically combined with shared memory for message passing. Thus, when a thread is interrupted by an inter-processor communication interrupt, it reads from the appropriate block of shared memory to retrieve a message from the thread that triggered the interrupt. A total of 16 interrupt IDs per CPU are available for inter-processor communication. From the point of view of an A15 core, an interrupt can be inactive. An inactive interrupt is one that is non-asserted or which in a multi-processing environment has been completely processed by that CPU, but can still either be either pending or active in some of the CPUs to which it is targeted, and so might not have been cleared in the interrupt source. A pending interrupt is one that has been asserted and for which the processing has not started on that CPU. There's active. An active interrupt is one that has been started on the CPU, but processing is not complete. An active interrupt can be preempted when a new interrupt of higher priority interrupts in A15 core interrupt processing. Interrupts come from the following sources. The interprocessor interrupts, IPIs. Each CPU has private interrupts ID 0 through ID 15 that can only be triggered by the software. The priority of an IPI depends on the receiving CPU, not on the sending CPU. Private timing and or watchdog interrupts. These use interrupts IDs 29 and 30. Legacy IFQ lines. In legacy IRQ mode, the legacy FIQ pin on the per CPU basis bypasses the interrupt distributor logic and directly drives interrupts requests into the CPU. Finally, there are hardware interrupts. Hardware interrupts are triggered by programmable events on associated interrupt input lines. CPUs can support up to 224 interrupt lines. Hardware interrupts start at ID 32. Figure 2115 is a block diagram of the GIC. The GIC is configurable to support between 0 and 256 hardware interrupt inputs. The GIC maintains a list of interrupts showing their priority and status. The interrupt distributor transmits to each CPU interface the highest pending interrupt for that interface. It receives back the information that the interrupt has been acknowledged and has then changed and can then change the status of the corresponding interrupt. The CPU interface also transmits end of interrupt EOI information, which enables the interrupt distributor to update the status of the interrupt from active to inactive. The MP Core's Snoop Control Unit, SCU, is designed to resolve most of the traditional bottleneck related to access to shared data and the scalability limitations introduced by coherence traffic. The L1 cache coherency scheme is based on the MISI protocol described in Chapter 20. The SU monitors operations with share data to optimize MISI status migration. The SEU introduces 3 types of optimization: direct data intervention, duplication tag RAMs, and migratory lines. Direct data intervention, DDI, enables copying clean data from one CPU L1 data cache to another CPU L1 data cache without accessing external memory. This reduces read and write activity from the L1 cache to the L2 cache. Thus, a local L1 cache miss is resolved in a remote L1 cache rather than from access to the shared L2 cache. Recall that main memory location of each line within a cache is defined by a tag for that line. The tag can be implemented as a separate block of RAM of the same length as the number of lines in the cache. In the SCU, duplicated tag RAMs are duplicated versions of L1 tag RAMs used by the SCU to check the data availability before sending coherency commands to the relevant CPUs. Coherency commands are sent only to CPUs that may update their coherent data cache. This reduces the power consumption and performance impact from snooping into a manipulating each processor's cache on each memory update. Having tag data available locally yet lets the SCU limit cache manipulations to processors that have cache lines in common. The migratory lines feature enables moving dirty data from one CPU to another without writing to L2 and reading data back from the external memory. This operation can be described as follows. In a typical MISI protocol, one processor has a modified line and another processor attempts to read that line. The following actions occur. One, the line contents are transferred from the modified line to the processor that initiated the read. 2, the line contents are written back to the main memory. And 3, the line is put in the shared state in both caches. The principal building block of the Z13 is the processor node. 2 nodes are connected together with an internode S bus and housed in a drawer that fits into a slot of the mainframe cabinet. A bus interface connect these 2 nodes with the nodes in another drawer. A Z13 configuration can have up to 4 drawers. The key components of a node are shown in figure 2116. This is what we're showing now, the processor unit, the PU. There are 3 PU chips, each containing 8 gigahertz processor cores plus 3 levels of cache. The PUs have external connections to main memory via memory control units and to I/O via host channel adapters. Thus, each node includes 24 cores. Storage control, SC, the 2 SC chips contain an additional level of cache, L4, plus interconnection logic for connecting to other nodes. DRAM memory slots provides up to 1.28 gigabytes of main memory. PCI slots, slots for connecting to PCI I/O drawers. GX++ slots for connecting to InfiniBand, S-band connection to other nodes in the drawer, A-bus connection to other drawers, processor support interface, PSI connect to the system control logic. The microprocessor core features a wide superscalar out-of-order pipeline that can decode 6 Z/architecture CISC instructions per clock cycle at a rate of less than 0.18 nanoseconds and execute up to 10 operations per second. Execution can occur out of program order. The instruction execution path is predicted by branch direction and target prediction logic. Each core includes 4 integer units, 2 load/store units, 2 binary floating point units, and 2 vector floating point units. So pretty complicated, and we're seeing really a high-end server type of application here. Next, the ZEC12 incorporates a 4-level cache structure. We look at each level in turn, and that's what we're showing here in figure 2117. Each core has a dedicated 96 kilobyte L1 I cache and a 128 kilobyte L1D cache. The L1 cache is designed as a write-through cache to L2 that is altered data are also stored to the next level of memory. These caches are 8-way set associative. Each core also has a dedicated 2 megabyte L2 split equally into 1 megabyte data cache and 1 megabyte instruction cache. The L2 caches are write through to L3 and 8-way set associative. Each 8-core processor unit chip includes a 64 megabyte L3 cache shared by all 8 core. Because L1 and L2 cache are write through, the L3 cache must process every store generated by the 8 core on the chip. This feature maintains data availability through a core failure. The L3 cache is 16-way set associative. The Z13 implements a embedded DRAM, actually an EDRAM, as L3 cache memory on the chip. While the EDRAM memory is slower than the static RAM, SRAM, traditionally used to implement the cache memory, the EDRAM can hold significantly more bits in a given surface area. For many workloads, having more memory closer to the core is more important than having fast memory. The 3 PUs in a node share a 480 megabyte L4 cache. The L4 cache is on a chip that also includes a non-data inclusive coherent NIC directory that points to L3 owned lines that have not been included in L4 cache. The principal motivation for incorporating a level 4 cache is that very high clock speeds of the core processors result in a significant mismatch with main memory speed. The 4th cache layer is needed to keep the cores running efficiently. The large shared L3 and L4 caches are suited to transaction processing workloads exhibiting a high degree of data sharing and task swapping. The L4 cache is 30-way set associative. The SC chip, which houses the L4 cache, also acts as a cross-point switch for L4 to L4 traffic up to the other nodes in the same drawer and to other drawers by bidirectional data buses. The L4 cache is the coherence manager, meaning that all memory fetches must be in the L4 cache before that data can be used in the processor. L4 caches use a line size of 256 bytes. The Z13 is an interesting study in design trade-offs and the difficulty in exploiting the increasingly powerful processors available with current technology. The large L4 cache is intended to drive the need for access to main memory down to the bare minimum. However, the distance to the off-chip L4 cache costs a number of instruction cycles. Thus, the on-chip area devoted to cache is as large as possible, even to the point of having fewer cores than possible on the chip. The L1 caches are smaller to minimize distance from the core and ensure that access can occur in one cycle. Each L2 cache is dedicated to a single core in an attempt to maximize the amount of cache that can be accessed without resorting to a shared cache. The L3 cache is shared by all 4 core on a chip and is as large as possible to minimize the need to go to the L4 cache. Because all the nodes of the Z13 share the workload, all of the L4 cache from a single L4 cache memory. So I'll say that again, because all the nodes of the LZ13 share the workload, all of the L4 caches form a single L4 cache memory. Thus, access to L4 means not only going off chip, but perhaps off drawer, further increasing access delay. This means relatively large distances exist between the higher level caches in the processor and the L4 cache content. Still, accessing L4 cache data on another node is faster than accessing DRAM on the other node, which is why the L4 caches work this way. To overcome the delay that are inherent to the design and to save cycles to access the off-node L4 content, the designers try to keep instructions and data as close to the cores as possible by directing as much work as possible of a given local partition workload to the cores located in the same node as the L4 cache. This is achieved by having the system and the Z/OS dispatcher work together to keep as much work as possible within the boundaries of a few cores in L4 cache space, which is best within a node boundary, as can be achieved without affecting throughput and response time, preventing the resource manager / scheduler and the dispatcher from assigning workloads to processors where they might run less efficiently contributes to overcoming latency in a high frequency processor design such as the Z13. So we're seeing a very, very complicated type of processor and computing environment here, just to give us a range. And we're finishing up our discussion on cores with that final example. So we talked about a variety of things. We talked about hardware performance issues, increase in parallelism and complexity, and power consumption. Those are the 2 things that can be addressed there. Talked about software performance issues, software on multi-cores. We talked about the value game software example, and so that was interesting to go through that. We've talked about a variety of different types of processors, ranging from fairly modest to fairly complex. We talked about the Intel Core i7-15960X, so kind of a workforce processor, the IBM Z13 mainframe. We talked about that at the end, the organization, the cache structure with 4 levels of caches. We talked about multi-core organization, the levels of cache, how we can be doing simultaneous multi-threading. We also talked about heterogeneous multi-core organizations, that there can be times where different types of implementation can have non-similar processing cores and take advantage of that by having some go to a less elaborate type of core that is more power efficient to something that's more capable, say like the ARM Cortex-A15. And we looked at that. And then we also looked at the ARM Cortex-A15 MP core. All right, well, that's going to finish up for this lecture, so thank you very much.